welcome to Digital to Real channel of mine. So, today I am going to design a synchronous counter. And the synchronous counter count in the sequence of 0, 1, 2, 3, 4, 5, 6, 7 and back to 0. And I am going to design the synchronous counter with the help of D flip-flop. So, let's start. How to design the synchronous counter is actually a sequential circuit. A sequential circuit which has a combinational block and a memory block. For the memory block, we are going to use the flip-flop and we are going to design the combinational block too. Why the synchronous? Synchronous means the output of the counter, all the output of the counter changes at the same clock edge, irrespective of the asynchronous counter. Now, as I showed, there are 8 stages. In order to have 8 stages of the flip-flop, how to determine how many flip-flops would be required? Now, 8 is equal to 2 raised to 3. So, we need to have 3 flip-flops. D flip-flop. Second step, we have to write the excitation table of the D flip-flop. The excitation table of the D flip-flop. What is Qn? Qn is the output of the D flip-flop at nth clock and Qn plus 1 is the output of the D flip-flop at n plus 1 clock. So, Qn is the present state while Qn plus 1 is the next state. The D flip-flop. Now, for D flip-flop, Qn and Qn plus 1, 2 bits. So, there would be 4 combinations 0, 0, 0, 1, 1, 0 and 1, 1. What does it mean? When the D flip-flop, that is the input to the flip-flop is 0 and the current value of the output of the flip-flop is 0, 2. So, what would be the next step, next stage or the next output of the clock, output of the D flip-flop at next clock? That is, it would be 0, 2. So, Qn plus 1 is 0. Second, input is 1, present state of the flip-flop is 0, next state will be 1. Input of the flip-flop is 0, but the present state is 1. But since the input is 0, next state of the flip-flop would be 0, 2. And the last one, input is 1, present state is 1 and the output of the flip-flop for next clock would remain at 1 itself. So you can see, based on the input of the flip-flop, the output changes. That is, the output of the flip-flop changes. Excitation table. Excitation table is actually derived from the truth table of the D flip-flop. As I explained earlier in excitation table, you can see that present state of the flip-flop is Qn and next state is Qn n plus 1. And D is the input to the flip-flop. So, when the input is 0, present state is 0, next state is 0. When input is 0, present state is 1, next state is 0 only. When input is 1, present state is 0, next state is 1. When the input is 1, present state is 1, next state would be 1. So, this is the truth table of the D flip-flop which is required in order to design the synchronous counter. This table is clear to me. Now, the third step is state diagram. State diagram of the synchronous counter. As I said, there are 8 states of the flip-flop. So, what would be the state diagram? You can see the state diagram. There are 8 stages or 8 states of the synchronous counter. It will make the transition from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7 and back to 0. This is the state diagram which I am going to design. State diagram is clear. Now the fourth step is I need to draw the circuit excitation table. Circuit excitation table for the synchronous counter. How it would be? You can see. So this is the circuit excitation table. I will have a 3-bit up counter. Though I have written it as truth table, but it is a circuit excitation table too. The present state and next state and D flip-flop output, D flip-flop input. So I have the present state, I have the 3 flip-flop. The present state output would be QP2, QP1, QP0. Next state output it would be QN2, QN1, QN0. And what would be the input to the flip-flops? D2, D1 and D0. You can see, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. And then is 1, 1, 1. So this is all I spoke about the present state. Now when the present state is 0, 0, 0, next state is 0, 0, 1. If next state is 0, 0, 1, then what would be the D2, D1, D0? It would be also 0, 0, 1. You derive it from the excitation table, where Qn, Qn plus 1 and D value we have written. You just refer to it and you will be able to make the circuit excitation table. Second state of the flip-flop is, second state of the present state is 0, 0, 1. So what would be the next state? 0, 1, 0, that is 2. And D2, D1, D0 would be 0, 1, 0. You can see to it, no? Now you can write it on your own, how it would be for the 8 states. I have written, when the 7th state is 1, 1, 1, next state it would be 0, 0, 0 and D2, D1, D0 would be 0, 0, 0, 2. Circuit excitation table we have drawn. The 5th state is, we have to obtain the simplified Boolean expression using the K-map for D2, D1 and D0. Let's see how it does. See, find values of D2, D1, D0 in terms of QP2, QP1 and QP0. Means present state of the D flip-flop and the input required to determine the next state. So you can see the K-map of D2. You can draw the K-map of D2. And I derive D2 as QP0, QP bar plus QP0, QP1 bar plus QP0 bar, QP2, QP1. Similarly, you can see I derived it for D1 too. So what I obtain is D1 is the simplified one, is actually QP2 XOR QP1. The K-map for D0 is shown. Can you see that? How it is? Can you simplify it on your own? Hopefully you can do, if you know how to simplify the K-map. So D0 which I obtained is at QP1 bar. Now the 3 Boolean expression after the simplification is D0, QP1 bar, D1, QP2, exclusive or QP1, D2, QP0, QP2 bar plus QP0, QP1 bar plus QP bar plus QP2, QP logic diagram. So we obtain the simplified Boolean expressions using K-map. Now we have to draw the logic diagram. So how to draw it? Now you can see there are 3 flip-flops. Clock is input to all the 3 flip-flops. Input to the first flip-flop is D0. Input to the second flip-flop is D1. And input to the third flip-flop is D2. Output of the first flip-flop is Q0, Q0 bar. Output of the second flip-flop is Q1, Q1 bar. Output of the third flip-flop is Q2, Q2 bar. Now how I am designing it? Now D0, did you see how the D0 Boolean expression are written over here? Now these are used in order to design the logic diagram. 3 flip-flops are there. And input to the 3 flip-flops are shown. D0, D1, D2, clock is shown. Same clock would be fed to 3 flip-flop. See, this 3 flip-flops, same clock is fed to all the 3 flip-flop. Now from the D0 you can see it is QP1 bar. Means Q1 for second flip-flop, present state P1 bar. That is here you can see that is Q1 bar. Q1 bar is being fed to D0. Can you see that? Second one is D1 QP2 exclusive or QP1. That is Q2. And Q1. Both are fed to the exclusive OR. And output of the exclusive OR, can you see? It is going to D1. You can see. Third one is, it is actually a OR of 3 AND gates. QP0, QP1, QP2 bar, QP0, QP1 bar plus QP bar, QP2, QP1. You can see how you can see, no? This is actually an OR gate, and 3 output of the 3 AND gate are going into the OR gate, and output of the OR gate is now going to D. Logical diagram will look like this. I will revisit what I have just discussed 1 minute back. 3 flip-flop, clock is going to 3 flip-flop, same clock, orange one, red one and pink one. These are all AND gates going into the OR gate, that is purple in color. Output of the OR gate is now going to D2. I have shown it with the pink arrows. D1, you can see it is the exclusive OR of Q1 and Q2. Can you see that with yellow color arrows I have shown? D0 is Q1 bar is going to D0. I have shown with red color, no orange color or arrows only. And Q0, Q1, Q2 are finally output of the circuit. You can see that this is how we have designed the synchronous counter, having 8 states, and the transition of the sequence is 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7 and back to 0. Thank you.